Quasars are among the most paradoxical creations of the cosmos, objects so distant, so ancient, and so powerful that they serve as lighthouses across billions of years of cosmic history. At their core lies not a star, not a galaxy, but a supermassive black hole devouring matter at a furious rate. The deeper the darkness at the center, the brighter the world around it becomes. This is the essence of a quasar, a young galaxy's nucleus ignited by a black hole millions or even billions of times more massive than our Sun, surrounded by a swirling accretion disk heated to unimaginable temperatures. Quasars outshine entire galaxies. Some emit more energy than trillions of stars combined, compressing that brilliance into a region no larger than our solar system. When the universe was young, just a few 100 million years after the Big Bang, quasars were the beacons that pierced the cosmic darkness. They illuminated the fog of neutral hydrogen, revealing the structure and composition of the early universe long before galaxies reached maturity. Their light, stretched by the expansion of space itself, now arrives to us as ancient messages written across billions of light years. They are violent engines, yet also delicate tools. Cosmologists use quasars as rulers of the universe, measuring distances, mapping the intergalactic medium, testing the limits of physics under extreme conditions. The brighter they shine, the deeper into the past we can see. In many ways, quasars are the universe's biography, written not in words, but in radiation, ultraviolet, X-rays, radio waves. Astronomers read those signals like pages of a cosmic chronicle, decoding how the first massive black holes formed, how galaxies grew around them, and how matter began its long journey from primordial chaos to the ordered structures we see today. And yet, despite their brilliance, quasars remain wrapped in mystery. Poetically, we might say, they shine brighter than trillions of suns, and all that light comes from the heart of absolute darkness. As we begin this journey, we will explore what quasars truly are, why they exist, and how their blinding radiance helps us measure, map, and understand the vast history of the universe. To understand a quasar, we must strip away the poetic glow and look directly at its anatomy, a structure unlike anything else in the universe. At its core lies a supermassive black hole, an object with a gravitational pull so extreme that not even light can escape once it crosses the event horizon. But the black hole itself is not what we see. The true brilliance of a quasar comes from the chaos swirling just outside that invisible boundary. Surrounding the black hole is a blazing accretion disk, a whirling maelstrom of gas and dust spiraling inward at nearly the speed of light. As this material falls toward the center, it heats to millions of degrees, releasing energy with astonishing efficiency. In fact, the conversion of gravitational energy into radiation in an accretion disk is far more efficient than any process in stars, far more than nuclear fusion itself. This is why a quasar can outshine an entire galaxy. A region the size of our solar system emits more power than hundreds of billions of stars. Outside the disk lies the dusty torus, a donut-shaped ring of molecular gas that obscures parts of the quasar depending on our viewing angle. It acts like a cosmic curtain, shaping what kind of quasar we observe, a bright unobscured beacon, or a more hidden active nucleus glowing behind veils of dust. Above and below the disk, two narrow relativistic jets erupt into space. These jets are among the most extreme phenomena known in astrophysics. Streams of plasma accelerated to nearly the speed of light, collimated by twisted magnetic fields around the black hole. Some jets stretch for millions of light years, punching through the intergalactic medium and depositing energy far beyond their host galaxies. They can ignite star formation in neighboring regions, or extinguish it entirely by heating the surrounding gas. A quasar is not static. It's a living engine, flickering and fluctuating as material spirals inward. Because the emitting region is so compact, quasars can change brightness on the scale of days, hours, or even minutes. This variability is one of the ways astronomers measure their size. A galaxy cannot change that quickly, but a compact accretion disk can. The faster the change, the smaller the region that must be producing the light. Taken together, the black hole, the incandescent accretion disk, the obscuring torus, and the relativistic jets, these structures form a single, unified machine. Every photon emitted by a quasar is the last scream of matter being torn apart, compressed, and heated in a final gravitational descent. And yet, from that destruction emerges light powerful enough to reach us across billions of years, a lighthouse shining from the dawn of time. Quasars do not appear randomly. They are the result of a cosmic sequence, a perfect alignment of conditions that once dominated the young universe. To understand how they ignite, We must imagine galaxies not as quiet islands but as turbulent clouds of gas still forming their first generations of stars. In the early universe, galaxies were smaller, denser, and far richer in cold gas than galaxies today. Hydrogen flowed along cosmic filaments in enormous rivers, feeding young proto-galaxies with material. And this cold gas, the raw fuel for both star formation and black hole accretion, was the essential ingredient for the birth of a quasar. A supermassive black hole alone is not enough. It must be fed, continuously and violently, in order to blaze. One of the most powerful mechanisms for delivering this fuel is galactic merging. When two galaxies collide, their stars pass through one another safely, but their gas does not. Gas clouds crash, compress, and ignite into starbursts, but more importantly, they lose angular momentum and spiral inward toward the galactic center. The collision shakes the entire structure of the galaxies, creating tidal tails, shock fronts, and vast flows of matter funneled directly into the region surrounding the central black hole. This inward cascade of gas triggers a dramatic transformation. What was once a quiet, dormant black hole suddenly becomes surrounded by a swirling reservoir of material. As the inflow intensifies, the accretion disk grows hotter and brighter, reaching temperatures of millions of degrees. Within a relatively short cosmological timescale, sometimes just a few million years, a quasar is born. The dormant nucleus becomes a brilliant engine, shining with the luminosity of entire galaxies. This is why quasars were most common in the early universe, roughly 1 to 3 billion years after the Big Bang. During this epoch, mergers were far more frequent, cold gas was abundant, and galaxies were still assembling their basic structure. Today, the universe is calmer, galaxies are more mature, the cold gas supply has dwindled, and mergers are less violent. The conditions that once created quasars have largely faded. Thus, quasars are not merely bright objects. They are signatures of a younger cosmos, markers of a time when galaxies grew through chaos, collision, and gravitational upheaval. Every quasar we observe is a fossil of that era, a lighthouse shining from a time when the universe was wild enough to ignite these cosmic engines. At the heart of every quasar lies a structure so violent and so elegant that no machine humanity could ever build approaches its efficiency. This is the accretion disk, a spiraling maelstrom of gas falling toward a supermassive black hole, heating itself until it glows brighter than trillions of suns. The physics behind its power begins with viscosity. Gas in the disk does not orbit peacefully. It rubs against itself, collides, shears, and twists. This internal friction forces matter to spiral inward, losing angular momentum as it falls. And every step it takes toward the black hole's abyss releases gravitational energy, not quietly, but explosively. The deeper the material falls, the hotter it becomes, converting potential energy into radiation with astonishing efficiency. A quasar's accretion disk can convert nearly 10% of the mass it consumes directly into light. For comparison, nuclear fusion in stars is only about 0.7% efficient. The temperatures inside this disk are extreme. Far from the black hole, gas glows in the thousands of degrees, emitting visible light and ultraviolet radiation. Closer in, the heat rises into the millions of degrees, so intense that atoms are stripped apart and electrons fly freely. In this inner region, the disk begins to radiate high-energy X-rays, providing astronomers with a direct window into the physics near the event horizon. These X-ray emissions flicker and pulse, revealing how matter moves in the final milliseconds before it vanishes. Because the disk spans a vast range of temperatures, its light forms a complex, multi-wavelength spectrum, from infrared to ultraviolet to hard X-rays. Each wavelength tells a different story. The cool outer regions whisper about incoming gas, while the blazing interior shouts about relativistic turbulence and the influence of the black hole's gravity. This is why quasars are perfect laboratories for studying the edge of the event horizon. They allow us to probe regions where space and time are distorted, where particles accelerate to nearly the speed of light, and where magnetic fields twist into shapes that defy intuition. No other known object produces such an accessible, continuous beacon of information about such extreme environments. To observe a quasar is to watch matter being torn apart, heated, compressed, and transformed into pure radiation, a cosmic engine operating at the limits allowed by the laws of physics. And despite the terrifying nature of its power, the accretion disk is also a source of beauty, a luminous storm orbiting an invisible core, revealing the geometry of space-time itself. If the accretion disk is the engine of a quasar, then the jets are its luminous exhalations, narrow, blazing beams of plasma launched from the poles of the supermassive black hole and hurled across intergalactic space. These jets can stretch for millions of light-years, forming some of the largest single structures ever created by nature. Their apparent superluminal motion, the illusion that parts of the jet move faster than light, is not a violation of physics. It is a trick of geometry and projection. When a jet speeds toward us at nearly the speed of light, its photons arrive in compressed intervals, making the motion look impossibly fast. In reality, no particle breaks the cosmic speed limit. The illusion arises because we witness the jet almost head-on. The light produced by these jets is equally extraordinary. It is dominated by synchrotron radiation, created when electrons spiral around magnetic field lines at relativistic speeds. This process generates a wide spectrum of emissions, from radio waves to X-rays, and gives the jets their characteristic glow. In radio wavelengths, these structures appear as colossal lighthouses, beaming their presence far beyond the host galaxy. But jets are not just visual wonders, they are architects of cosmic evolution. As they plow through space, they carve cavities in the surrounding gas, inject energy into the intergalactic medium, and regulate the growth of galaxies. In massive galaxy clusters, jets inflate enormous bubbles of heated plasma, preventing gas from cooling and collapsing into new stars, a phenomenon known as AGN feedback. Without this process, galaxies would form far more stars than they do today, burning through their fuel too quickly. Jets also redistribute heavy elements and magnetic fields, enriching the cosmic environment far from their origin. They are engines of change, shaping the ecology of the universe on scales so vast that even entire clusters feel their influence. To see a quasar jet is to witness a bridge between the smallest regions of extreme gravity and the largest structures in the cosmos. A thread of energy stretching from the edge of a black hole's event horizon to the silent darkness between galaxies, a cosmic searchlight pointing into infinity. Quasars are not only the brightest lighthouses in the universe, they are also time machines, carrying messages from an era when galaxies were still young and the cosmic web was just beginning to take shape. Their light travels across billions of light-years, passing through vast stretches of intergalactic space before reaching our telescopes. And every cloud, filament, and wisp of gas along that path leaves a signature imprinted on the quasar's spectrum. This is why quasars are called cosmic beacons. They illuminate what would otherwise remain invisible. As quasar light journeys toward us, it encounters the thin fog of hydrogen and helium between galaxies. Though extremely diffuse, this intergalactic gas absorbs specific wavelengths of light, creating narrow notches known as absorption lines. The most famous of these is the Lyman alpha forest, a dense series of spectral lines, each one marking a cloud of ancient hydrogen drifting somewhere along the line of sight. By studying these lines, astronomers can map the temperature, density, and chemical composition of the universe at different epochs. The spectrum of a quasar is therefore a layered historical record. The farther the quasar, the older the snapshots it provides. A quasar at a redshift of 6 reveals the state of the cosmos just a few 100 million years after the Big Bang. Its light passes through primordial filaments, through gas collapsing into the first protogalaxies, through the cosmic web still forming its massive skeleton. Absorption lines shift depending on the motion of the gas, allowing researchers to detect inflows, outflows, and early galactic winds that shape the emerging universe. Even the absence of certain lines is meaningful. It tells us when the universe transitioned from neutral hydrogen to ionized gas during the epoch of reionization, a key transformation in cosmic history. Quasar light thus becomes a probe for understanding how the first stars and galaxies altered the universe around them. Through a single quasar, we can detect galaxies too faint to see directly, map structures billions of light-years long, and identify ancient gas clouds that collapsed to form the first generations of stars. No other object gives us access to such vast distances and such deep time. To observe a quasar is to shine a flashlight backward across the entire universe. It reveals that the cosmos is not empty space, but a complex, evolving landscape, a tapestry of flows, filaments, voids, and forgotten clouds, all written in the faint shadows cast upon a quasar's light. Quasars are not quiet lighthouses. They are storms, titanic engines powerful enough to reshape entire galaxies. When a supermassive black hole feeds aggressively, the energy it releases does not remain confined to the accretion disk. It erupts outward, driving colossal outflows of gas known as quasar winds. These winds are not gentle breezes. They can reach thousands of kilometers per second, fast enough to escape the gravitational grip of entire galaxies. Spectral observations reveal gas being blasted outward at relativistic speeds, ionized by intense radiation and pushed by the fierce pressure of the quasar's light. What emerges is a dark, invisible hurricane, one that carries molecular clouds, dust, and metals across interstellar and even intergalactic space. This violent process has profound consequences. Gas is the fuel for star formation. Remove it, and a galaxy cannot give birth to new stars. When a quasar turns on, it becomes capable of quenching its host galaxy, shutting down star formation on cosmic timescales. This is why galaxies with the most massive black holes often appear red and dead, filled with old stars but no new ones. The quasar has literally blown the cradle empty. This is where the principle of self-regulation emerges. A black hole does not grow unchecked. As it feeds, it generates powerful winds that expel the same gas it needs to consume. Eventually, the outflow becomes strong enough to choke the accretion process, reducing the black hole's supply and forcing it into dormancy. In this way, the black hole indirectly controls its own growth and the evolution of its galaxy. This feedback loop mirrors what happens in other active galactic nuclei, AGN, but quasars demonstrate the process on the grandest scale. Their winds can carve tunnels through the interstellar medium, heat galaxy halos to millions of degrees, and enrich the surrounding cosmic environment with heavy elements forged inside ancient stars. They become engines of galactic transformation. To study a quasar wind is to witness the balance point of cosmic ecosystems, a single compact object shaping the fate of billions of stars. It is a reminder that in the universe, power is often hidden in the least expected places, deep within a gravitational abyss, capable of breathing storms across the cosmos. The James Webb Space Telescope has revealed one of the most unsettling puzzles in modern cosmology. As it peers back to the first few hundred million years after the Big Bang, JWST is finding quasars at redshifts Z almost equal to 7 to 10, objects so distant that their light has traveled more than 13 billion years to reach us. And yet these quasars are not small, fragile seeds of future galaxies. They are cosmic giants. Many of the quasars discovered by JWST already host black holes with masses between 1 and 2 billion suns. In the early universe, a universe still assembling its first galaxies, still cooling, still forming its earliest stars, such enormous black holes simply should not exist. According to standard growth models, a black hole needs time, millions of years to form, hundreds of millions to grow, and steady access to gas to feed on. But at redshift 10, only a few hundred million years have passed since the universe began. There should not have been enough time for gravity to accumulate so much mass. This is known as the black hole growth problem, one of the most significant cosmological tensions strengthened by JWST's observations. If ordinary stellar mass black holes began forming from the first generation of stars, they would have needed to accrete gas at a steady, moderate rate. But those conditions could not produce billion solar mass monsters so quickly. Something else must have happened. One possibility is super-Eddington accretion, a phase in which a black hole grows faster than traditional physics predicts. In normal circumstances, radiation pressure created by infalling matter pushes outward, limiting how quickly a black hole can feed. But there may be brief episodes where gas plunges inward too rapidly for radiation to escape, allowing the black hole to devour mass at extraordinary speed. For early quasars, this extreme feeding might have persisted long enough to build up enormous masses in record cosmic time. Another explanation is far more dramatic: direct collapse black holes. Instead of starting from a small seed left behind by a dying star, some black holes may have formed when entire primordial gas clouds, hundreds of thousands of solar masses, collapsed directly under their own gravity. Without fragmenting into stars, these pristine clouds could have produced initial black holes already weighing 100,000 suns or more. From such massive seeds, growing into billion solar mass quasars becomes significantly more plausible. Both scenarios remain speculative, but JWST's findings suggest that the early universe was more dynamic, more chaotic, and more efficient at creating cosmic giants than we once believed. Whether through runaway accretion, direct collapse, or an unknown mechanism yet to be discovered, the earliest quasars challenge our understanding of how structure emerged from the darkness. They are beacons from a time we barely comprehend, reminders that the young universe was capable of feats that still defy our theories. Quasars do not appear randomly across the universe. They sit at the nodes of the cosmic web, the great intersections where multiple filaments of dark matter and gas converge. These nodes are the regions with the highest density of matter, acting as gravitational basins that funnel gas inward over hundreds of millions of years. For a quasar to ignite, a black hole must be fed, and nothing feeds a growing black hole better than the deep cosmic highways that channel material from vast intergalactic distances. In this way, quasars become natural signposts of the largest structures in existence. Wherever the web knots itself tightly, a quasar may blaze to life. As their brilliant light travels toward us, it passes through enormous stretches of intergalactic medium. That light becomes a flashlight shining through the universe, revealing what the naked eye could never see. Every cloud of gas, every filament of dark matter a guided structure, every early protogalaxy leaves its signature imprinted onto the quasar spectrum. Astronomers call this the Lyman alpha forest, a series of absorption lines that act like shadows cast by the cosmic web itself. Through these shadows, quasars illuminate the architecture of the universe on scales far beyond any single galaxy. This is how quasars become powerful tools for mapping the growth of structure. By observing many quasars spread across the sky, scientists can reconstruct a three-dimensional picture of the cosmic web in the early universe. The light they emit allows us to detect protoclusters, the ancestors of today's galaxy clusters, long before they collapse into dense, gravitationally bound systems. Regions where the absorption lines are especially strong or clustered together mark places where matter is gathering, forming the seeds of future superclusters. Some of these structures stretch tens or even hundreds of millions of light-years across, and quasars help us glimpse them when they were only beginning to take shape. In this sense, quasars are more than cosmic lighthouses. They are messengers from the architecture of the universe, revealing where its skeleton is densest and where the grandest structures are being born. Their light allows us to trace the silent scaffolding of dark matter, to witness the spots where galaxies will gather and clusters will emerge. Through them, the invisible becomes visible, and the cosmic web, normally hidden in darkness, unfolds in luminous detail. Quasars, among the brightest objects in the universe, serve not only as distant beacons but also as natural time lenses. When their light travels across billions of light-years, it often encounters massive objects along the way, entire galaxies or galaxy clusters whose gravity bends space-time itself. This bending causes gravitational lensing, an effect predicted by Einstein and now observed with extraordinary clarity. The warped space-time acts like a cosmic magnifying glass, stretching, brightening, and even duplicating the image of the quasar behind it. In some cases, a single distant quasar can appear as 2, 4, or even more separate points of light, a phenomenon known as multiple imaging. These images are not different quasars, they are the same object, seen along different curved paths through space-time. Each path has a unique length and gravitational depth, so light from each route takes a slightly different amount of time to arrive. This creates time delays between the flickers of brightness we observe in each image. When the quasar fluctuates, as quasars often do, those variations appear in each lensed image at different moments, like echoes across cosmic distances. These delays are not just curiosities, they are powerful scientific tools. By measuring them precisely, astronomers can determine the geometry of the universe and even calculate the Hubble constant, the rate at which cosmic expansion unfolds. Gravitationally lensed quasars therefore become natural laboratories for studying the growth of space itself. They show us how the universe bends light, warps time, and stretches distances, transforming quasars into instruments that reach far beyond what any human-made telescope could currently achieve. In this way, a single quasar becomes more than a distant light. It becomes a cosmic clock, a ruler, and a magnifier all at once, revealing how space-time behaves on the grandest scales and helping us trace the silent expansion of the universe. Quasars do not shine forever. Their brilliance depends entirely on a supply of cold gas spiraling toward the central supermassive black hole, and once that fuel thins out, the engine begins to shut down. Over millions of years, the surrounding galaxy gradually exhausts its reservoirs of gas, either by forming stars, by being blown out through powerful quasar-driven winds, or simply by settling into a quieter, more stable configuration. When the inflow toward the black hole weakens, the once blazing accretion disk dims, its temperature drops, and the jets lose their power. The transformation is slow on human timescales but rapid in cosmic terms. As the luminosity fades, the galaxy transitions from an active quasar into an ordinary, quiescent system where the central black hole becomes mostly silent. What remains is a massive elliptical or spiral galaxy with a dark, dormant core. Many astronomers believe that the Milky Way itself passed through such an active phase billions of years ago, when abundant gas in its youth may have ignited our own central black hole into a brilliant quasar-like outburst. Today, Sagittarius A* is quiet, a sleeping giant that flickers only occasionally, but in the distant past, it may have lit up half the sky. The lifespan of a quasar is relatively short, typically 10 to 100 million years, a fleeting moment compared to the age of the universe. During that time, quasar activity shapes the evolution of its host galaxy, regulating star formation, redistributing gas, and altering its future trajectory. When the fuel is finally gone, the galaxy settles into long, calm ages where stars form slowly and the black hole waits silently for the next influx of matter. In this way, the death of a quasar marks not an end, but the beginning of a quieter chapter in a galaxy's life, one shaped by the memory of its brilliant and turbulent youth. Quasars are more than brilliant beacons. They are messages from a universe that no longer exists. Their light has traveled billions of years to reach us, crossing epochs in which galaxies formed, collided, and changed beyond recognition. When we observe a quasar, we are not seeing an object as it is now. We are seeing it as it was when the cosmos was young, when stars were still gathering into their first grand structures and the night sky looked entirely different from today. In this sense, quasars act as time capsules, silent witnesses of an early universe, carrying within their radiation the history of everything their light has passed through. Quasars are letters from the past, written in the fire of black holes, a reminder that even the most violent engines of the cosmos can illuminate our path across time. Their brilliance helps us map the structure of the cosmic web, trace the evolution of galaxies, and understand how the first heavy elements were forged. They reveal the chemistry of intergalactic clouds, the growth of supermassive black holes, and the hidden architecture of the universe stretching far beyond the reach of telescopes alone. In the vast darkness between galaxies, quasars serve as the brightest lighthouses we have. Without them, the early universe would remain largely invisible, a mystery shrouded by distance and time. But with each photon that reaches Earth, they peel back another layer of the cosmic story, showing us what the universe looked like when it was still young and raw and full of possibility. And so, the study of quasars becomes more than an exercise in astrophysics. It becomes a way of listening to the universe's oldest voices, echoing across the abyss. These distant giants remind us that light can survive unimaginable distances and unimaginable time, and that even in the deepest darkness, the cosmos always finds a way to speak.